All right, in today's class we're looking at bond enthalpies. Normally when you add energy to electrons, you promote them to higher level orbitals, and then when they fall back to those orbitals, they are known to give off their energy, and they fall back into the normal orbital that they occupy, which they call the ground state. A lot of times electrons are also involved in bonding, and when you promote the electrons in a bond out to a higher energy level, you can actually break the bond. So there's a certain amount of energy that goes into doing that. The average bond enthalpies can be calculated for gaseous molecules and are useful for estimating reaction enthalpies. And enthalpies is just a fancy word for the heat energy contained in the chemical substances. When molecules react, the breakage of bonds requires input of energy. So if you want to break a bond, you've got to put work into it. You have to put energy into it to break the bonds, to separate the two atoms. The formation of bonds releases energy. So when you have a chemical reaction, two things are happening. You're breaking bonds in the reactants, and you're forming bonds in the product. And you could do an accounting of a typical reaction to give an estimate of how much energy is going to be released by the reaction. I use the example here of the burning of acetylene. Acetylene is the fuel of choice if you want to make a welding torch burn, because acetylene burns at a very high temperature. So what they have typically in an acetylene torch are two knobs, one for the acetylene, one for the oxygen. You can adjust the mixture so the flame gets really hot, and you can actually cut steel rods or anything you like with it, or you can weld. I balanced the equation for the burning of acetylene and oxygen. Whenever you burn a hydrocarbon, you get two things, carbon dioxide and water. And these numbers here mean the stoichiometry of the reaction, meaning how many moles of acetylene is necessary to be burned with how many moles of oxygen to get the 4 moles of carbon dioxide, 2 moles of water. And just briefly, we'll see that if there's, you can start over and rebalance it just for fun and practice. If you have an acetylene molecule, there are 2 carbon atoms in the acetylene molecule, so you need to have 2 carbons appearing in some form or another as a product, in this case carbon dioxide. There are also 2 hydrogens in acetylene, which also have to appear in some form in the product side of the equation, so we can put 1 water molecule. And then if you look at the number of oxygens that appear on the right-hand side, you're going to have 4 plus 1 over here, that's 5 oxygen atoms. They come, and oxygen atoms are diatomic, so if you put a 5 here, you'll get twice as many as you need. So let's just put put the 5 over a 2, and it halves the amount of oxygens that you're using. Some people get nervous when they see fractions in a chemical equation. So if that bothers you, just double everything. Put a 2 over here, 5 over 2 turns into a 5, this turns into a 4, and this turns into a 2. And these numbers represent what's called the stoichiometry of the reaction. 2 molecules of acetylene will combine with 5 molecules of oxygen to form 4 molecules of carbon dioxide and 2 molecules of water. You could also say 2 dozen acetylene molecules will combine with 5 dozen oxygen atoms to give you 4 dozen carbon dioxides and 2 dozen water molecules. But in chemistry, we use a word called the mole. And the number is not 12, it's 6.02 times 10 to the 23. That huge number is used because atoms are very small. So the chemist's dozen is that number. It's called Avogadro's number. You're going to learn about that later. What we're really looking at here is how bonds are breaking, and that requires input of energy, and bonds are forming, which requires energy which releases energy. If we move on to the next board, and if you would be kind enough to tilt the camera somewhere, we'll see that I've taken account of the bonds that are breaking and the bonds that are forming. We'll see here that acetylene, because I balanced it, I put a 2 on the outside with the bracket to show that 2 of these molecules are breaking, 5 of these molecules are being broken, 4 of these are forming, and 2 of these are forming. So I looked up the table on page 330 of our textbook, and they have a listing of what the energy content of each of the bonds is, and how much energy it takes to break them. So here, because we're breaking all the bonds, I added up all the quantities, and it takes 5,805 kilojoules to break all the bonds on the left-hand side of the equation. On the right-hand side of the equation, all these bonds are forming. So then I tallied how much energy that would release. It came up to 8,244. Now if I subtract this number from that number, then I'll see how much energy is actually produced as a net amount, and that's what we get here. 2,439 kilojoules of energy is released for every 2 moles of molecule of acetylene that's broken. You see there's a 2 here, so we have to say that's for 2 moles of molecules. So if I divide this number by 2, I'll find out what it is for 1 mole. So for every 1 mole of acetylene that's burned, we get roughly 1,219 kilojoules of energy being released according to this rough estimate. Now this calculation works for gaseous atoms, and it gives you a ballpark. It's not always 100% accurate. We'll find out in chapter 5 that they use enthalpies of formation, and that gives you a more accurate result. At any rate, you'll notice I put a negative sign in front of this number. Why? Because it's energy that's released. And the sign convention is that when a reaction is exothermic, it means that heat is released, so we put a negative sign in front of it. If energy is being absorbed, then it's called endothermic, and we put a positive sign in front of the number. So this number is going to have a negative sign because that much energy is being released. Now let's do another example. This is from the textbook itself. It's Brown, page 333, the practice exercise. They ask you, this molecule breaks down into nitrogen and hydrogen gas. I think that's called hydrazine. And we do an accounting of all the bonds being broken. So the nitrogen bond is being broken, and 4 hydrogen atom to nitrogen bonds are being broken. So the amount of energy that's got to be inputted to make that happen is 1,727 kilojoules per mole. You might ask yourself, how does a fire get started if it takes that much energy to break the bonds? Well, 2 things. First, you've got to input some kind of heat in the form of a spark, or at least in the form of kindling. A small flame will get the reaction started. Once the reaction starts, then this half of the equation starts to take over because it starts to release energy when new bonds are forming. When new molecules reform that have a low energy, but which are releasing the energy as the bonds form, that's what's supplying the heat for the fire to continue getting bigger. So breaking all the bonds in this molecule involved here requires an input of 1,727 kilojoules, and all these bonds that are being formed release 1,813. So when you subtract the input of energy from the amount of energy released, you get 86 kilojoules of energy. And then you should report the answer as an exothermic one, so it's going to be negative 86 kilojoules as a final answer. Negative 86 kilojoules of energy is released for every mole of this molecule that is broken down. We'll stop it there.